Welcome y'all to another episode of our Shenzhen I Let's Play. This will be episode 9. Last week you'll remember we completed the remote kill switch. So it ended up being a pretty straightforward solution when we were able to use a creative way to keep track of our state. I really wish I could figure out how to do that all on one chip though. But let's go take a look at the control router. Yep, same as last time, civic infrastructure, smart grid, blocking XBus inputs, which is different. So it'll be interesting to see how this works out. Okay, so this apparently has our ID number in it. Okay, so we have higher end, meter end, lower end. If a packet bound for a higher meter comes in, we're supposed to send it to the higher out. And if it's lower, goes to a lower out. And if it equals us, then we send it right back out. So it sounds like they're trying to do some kind of like mesh network type deal, where as long as you hook up the inputs correctly, then everything should just work out. A couple things to note here, we have 6 XBus inputs and outputs. 7 if we count our ID that's on that little lock chip there. And just doing a quick little check, let's see how many packets there are for each thing real quick. Oh, that's a lot of packets. Where does it talk about the packets? Okay, so the first packet is the ID, and the second value is the length of the rest of the data. Pretty common practice way of handling that. So we're going to need a transmit loop and a greater than or less than kind of a deal. Let's just do a quick guesstimate on the number of lines. Here, let's throw it on a chip and write some of this out real quick. But I'm thinking at least this is going to take 2 chips. And another fun thing about XBus, we can do that. And then the packet will just get routed to us. So we needed to save off the first 2 packets. So we are going to, this is going to be our start. We're going to sleep until we get a packet in X0 because it's blocking for once, which is nice. We're going to move whatever data we get to the DAT. And then we're going to move the second packet to the accumulator. Yes, we want to do it that way because we want to have the second packet go to the accumulator because that's the length. So that'll be used for our loop on how many times we need to loop, for how many more packets there are. I'm wondering if you could get away with some kind of a sleep. I don't think you can. I mean, you could just sleep until you get data and then send it out. Problem with that though is that you wouldn't know when it was time to reset and start where the first packet will be the ID again. It's one of the fun things about being low level like this. Everything's the same, it's just a bunch of bytes. So it's hard to infer things about it outside of keeping track of your state and doing things like that. Okay, so let's check to see. So that's 3 lines there just to get it in. Now to write this out, it's going to be another 3 lines. So another move and another move just for the DAT and the accumulator. And then we'll need a loop over all that, either out somewhere or somewhere else. So we'll need a check to see which way we're looping. So let's just say the DAT equals us. And we'll wire that up to X1. And now we need to do our loop, which will start with us figuring out which way to route the things. So let's say loop dir, and then call this dir1, dir2, and then we subtract 1 from our counter, and we check to see if accumulator greater than 0, as then we still have more stuff to move, and then we jump back to loop. So yes, I think we're going to need more than 1 chip for this. And I think we can basically just duplicate the code to where we know which way it needs to go. So let's go ahead and try that. So let's wire this computer up. And say that is equal to X1. Let's have X3 just write out to the meter. We need to write out our ID or the destination ID, and then we need to write out the number of packets. If not, then we'll write it out to X2 because that's the only XBus pen we have left. Write that to X2, and then write the accumulator to X2. Now we need to do our loop. And if if x1 is equal to the dat. Then we want to move these packets out to x3. Otherwise, we want to move these packets to x2. Sub1, then we need to see if the accumulator is greater than 0, and if it is, jump back to our loop. Now for chip 2. You can go there, you can go there. So we start out the same way. We know it won't be equal. What we want to do is test compare. If the first thing we're testing is greater than the second thing we're testing, it'll activate the pluses. If they're equal, it won't do anything. And if it's less than, it'll activate the minuses. So then what we want is if the dat is greater than x1, we'll need a bridge. You can go there. So if the dat is greater than x1, we move everything out to x3. Otherwise, we move to x2. Again, dat greater than 1. And actually, this needs to be TCE. And then, so move x3. Yes, that's correct. Move x0. That's correct. Sub1 and everything else. Aim. All right, give that a go. Yep. Like it works. I mean, I'm just trying to think of something simple we could do to drastically reduce the number of lines of code, and I am not seeing it. Yeah, that'll work for today. So again, she's really pushing to get this guy's business. I think she thinks that there's a lot there for us. Ooh, a meat-based printer. That sounds fun. Let's go take a look at the Pocket I Ching Oracle. Basically, he wants a more realistic way of generating the readings, or a more authentic way, and is okay with a model, even though it's still a model and not going to be exactly accurate as doing the real thing. Okay, I'm not one to judge. Well, I try not to judge. Just doing a quick look, we have 6. That looks like a nice place for 2 digital I/O expanders. And then we have, I think that thing is a button and then has also the magic MEMS modeling on it. Let's go take a look at the verification. Ooh, okay, that makes this a bit more difficult. We have to loop over the 6 cycles after the button is pressed. That unfortunately makes this a bit more difficult than you would think. What we need to do is we need to set up a edge detection thing to where we loop until we see 100, and then we need to kick off a read loop of 6 cycles. And then something else needs to take that and output that. Unfortunately, I don't see some easy way of kind of splitting this up. I do think that we're going to want/have to use the digit set. And unfortunately though, trying to do the digit set is going to be difficult for 6 different values. I mean, arguably we could split that up between 2 chips. Let's just think about it real quick and look and see how many lines that's going to take by itself. 0, x0. I'm assuming we're going to read this in. Then we have to move that off. And then we have to do that again. And then move that out to somewhere. Let's just say x3. And then move the dat to x3. So what is that? 6, 7, 8, 9 lines? I mean, we could fit that on a small chip. That's not even doing any flow control of knowing when to sleep and when to not and all that stuff. So we're going to need to, I mean, this in and of itself, we're going to have to split this up. If we're smart, we might be able to split this up in a way to where we can actually loop the setting of those values instead of having to have that split out. Because if we have any kind of flow control here, this isn't going to work. And what I think we can get away with doing something silly and having one chip just read in the values and pass them over to the other chip, and the other chip just uses that data to set the different digits, and then at the end it'll write it all out. So let's see what we can do with it. Get rid of you because it's faster than just clearing it, and let's set up our digital I/O expanders. So now here's one downside to the fact that they changed it to being this display down here instead of individual IO lines, is I don't know which one's which. Well, we don't really see it there either. I guess it'll explain it over on the information tab, so let's go look there. Yeah, it doesn't tell us. Look at the digital IO lines. Since it's 0 to 2 from bottom to top, I'm going to assume 0 is the bottom line, or line 0, and the top one is the highest line, line 6. Or line 5, actually, in this case. We'll have to check it out and figure it out. I really assume that, because otherwise this would be a pain to flip everything around, and it'd be really weird to write it otherwise that way. Actually, I don't think it'd be too bad to flip it around. We would just have to change the order that we're setting the digit. We can just roll with this, and then if it's backwards, we'll fix it. All right, let's move this one up here. And as usual, we'll start with the big chip. 4-3. Okay, so you can go there, you can go there, you can go there. Oh, wait, no. That won't work. Move this there, this there, there. That won't work because we need to have this line go up here. And then we're gonna need this line to come out here. Okay, so now first things first, let's set up our reading in bit and then seeing what we can do. So first things first, we need to wait until we get a high value from P1. If we don't, we sleep one and we jump back to wait. Pretty standard. Almost gotten to the point where I can copy and paste that code just about in a lot of these puzzles. But welcome to programming. After that, we can move a 6 to the accumulator. And then we can set up our read loop. And wait until the accumulator equals 0. And if it's not 0, then we need to read, so we can move E0 to X3, because we're going to just let that one handle it. We can subtract 1 and sleep 1, and then jump back to loop. Looks like that's only 9 lines, which is nice, so that we can move that to a smaller chip if this works. But we first need to see if this will work before we start doing any kind of premature optimizations. Now for the fun part. We need to keep track of our state so we know if we're reading the first set or the second set. We can't use 0 for that, because 0 is a valid value for what the DAT could be as a final value. Fortunately, we have negative numbers, so let's move -1 to the DAT. Since, again, like I was explaining last time, that could never be an actual value, so it's a great way to say we are not set yet. And then we need to wait until we get a value from X1, so we'll sleep until X1. So then we need to digit set the first digit from the value read in on X1. Then we can sleep until the next value from X1. And just repeat until we have all of them. We could have used the accumulator to keep track of our counts so that we can just increment that to go through all the digits. Unfortunately though, then we would lose what our values are. So that wouldn't really work. And unfortunately, using the get digit clears out all the other numbers in the accumulator, which kind of makes it not very useful. Or at least I haven't found a good use for it. I mean, I guess typically, well, on most things, you would either have more registers or you would set that as like a sub function. Either way. So we set all of our things. Now we need to check to see if we're the first number or the second number. We're the first number, so test equal -1 to the DAT. If we are, we want to move the accumulator to the DAT and jump back to the start. Otherwise, we are not. So then we'll move the DAT to X2 first, because remember, we're assuming bottom top. And then we'll move the accumulator to X3. So let's see how that works. Okay, so far so good. Oh, we messed up some. What did we mess up? We should have gotten our last number here. We did write out the value. We write out the value. Both of those numbers were wrong. I think is the problem here. So where did we mess up? Oh, I see the problem. Okay, we're moving hundreds. And that apparently does not work well with digit set. So we need to convert that to a 1. Is there a way we can do that without actually having to do more lines of code? Because if we add more lines of code, we can't drop the size. What if, it'd be kind of wasteful money-wise, but we'd still save 1 yuan using a digital I/O expander instead of so we can just put that there, and we'll still save 1 yuan converting that big chip down to a smaller chip than we would having 2 big chips with the extra lines of code we would need. Okay, why do you say that? Oh, that's why, because that's a... We don't want P0 anymore. We want X1. And so let's give that a shot now. Yes, that seems to work a little bit better. Ooh, hey, it's actually working totally. Lines of code was a bit much, so was power usage. Go drop this down to a smaller chip real quick and see if that helps at all. I'm going to guess it's not going to help with any of that except production cost. Oh, so how are you going to be? You're going to be... This will need to change to here, right? 0x1. Yes. And this will need to be x0. Or sorry, x1 and x0. And that looks like that's all that needs to change. So this can go away. Give that a shot. Yeah, power usage was still the same. Lines of code was still the same. Production cost went down by 2. Why did that go down by 2? Oh, derp. Because I already had the digital I/O line in there, so of course it would go down by 2. Which helped, but apparently we could have done better. I'm curious what we could have, how we could have done better. I'm betting if we use the logic gates to set up some kind of latch so we know when to run and when not to. I really still need to look into the logic gates and see how we can set up various latches and whatnot, because I know they can be useful. But I'm wondering if we could have gotten our production costs down below 3 with that many gates. We'll save it for later. So David seems to be pretty excited about it. And I think that was a bit of a jab that J, let's go with J, since that's what Carl called him the other day. I don't think David quite caught the jab that Jay is making there. With that, if you like, leave a like. If you didn't, leave a dislike. If you have any questions, suggestions, feedback, or advice, drop it in the box below. Good luck in your races, and y'all take it easy.